Thank you so much for taking the time to review my presentation. Tonight's presentation is called Leave Your Phone at the Door, Side Channels that Reveal Factory Floor Secrets. So this is a collaborative paper written by Hajjati et al. And believe me when I say et al, there was probably 8 different authors that contributed to this really interesting paper. My name is Stephen Smith. I'll be presenting the paper as a review and as an assignment for cyber physical system security for the spring 2020 semester. Like any academic paper, it's a good idea to always take a look at the abstract first and also pay close attention to the conclusion section. You can get a really good idea of what the paper covers. So on this slide, let's go ahead and talk very briefly about a high-level overview of what this paper is about. And from summarizing the abstract summary itself, design and manufacturing processes are expensive corporate endeavors, and because of that cost, many bad actors are motivated to steal intellectual property. This paper discusses that one way individuals can steal intellectual property is by using what's called a side channel attack via a cell phone with attack-enabled software. And this paper focuses on a sample application of a cell phone-enabled side channel attack on a 3D printer and a CNC mill. There's a lot of content to cover in this presentation, and overall in this presentation I'll describe how Hajjati et al., that team of researchers, demonstrates this attack. I'll also give you background information of cyber attacks in the manufacturing industry in general. I'll furthermore go into describing the experimental setup used in this study, discuss the results of the demonstration that was presented in this paper, and finally highlight recommendations that the authors make to help industry leaders and their technical staff avoid falling victim to this side channel attack. Like so many things in cybersecurity, knowledge is power, and it's so important to be able to get the information out there so that people that have spent millions, and in the case of the government, sometimes billions of dollars of research and development money to come up with manufacturing processes and things like that that could be grabbed or acquired from a hostile actor. It's so important to know this information and to act accordingly. So I wanted to provide a little bit of background detail. Before I read this paper, I think I'd read about side channel attacks before, but I didn't really know a whole lot about it. So as sort of a sidebar to the contents of this paper, I did a little bit of extra research, and that's cited below, of what is a side channel attack. And when the PURUP 2019 article talks about that, they say to enter side channel attacks. And that's a type of an attack that can break cryptography. That's one extension of a side channel attack by using information leaked by cryptography, such as monitoring the electromagnetic field or EMF radiation emitted by a computer screen to view information before it's encrypted, like a Van Eck freaking attack or a transient electromagnetic pulse emanation standard or Tempest attack. Other well-known side channel attacks include spying on power consumption of an electronic device to steal an encryption key, or acoustic attacks that record the sound of a user's keystrokes. So these side channel attacks are not theoretical, and they've been known for a long time. The oldest and probably the most common used by intelligence agencies and police around the world is where they park the van across the street from a victim and spy on their computer screens using a Tempest attack. The other thing that you'll note in this diagram is I did provide sort of a low-cost side channel attack design overview based on a malicious peripheral. And the reason why I wanted to include that is that it'll sort of serve as a segue for what this whole paper is actually covering. So you'll notice when I talked about side channel attacks and defined it based on the paper, they were talking about it in terms of an attack against cryptography. But really, in the manufacturing industry, hackers can use side channel attacks on manufacturing floors, and they can steal sensitive data by detecting electromagnetic leaks, sound emissions, timing information, light emission, and power consumption. And based on these high-level system and attack models, by using phone sensors in proximity to a manufacturing process, the side channel actually can help hackers reconstruct the design and manufacturing process. This is something I had no idea about before I read this paper. I thought it was really fascinating. I also wanted to include the figure that you see on this page as well, where it gives you an idea that in the manufacturing circles and in the R&D environment, you start with a design, develop a manufacturing process, and you end up producing a completed part. Here, you can start with materials if you're a hacker, and through an elaborate use of sensors and reconstruction, you can actually recreate that design or recreate the process. And then all of a sudden, as a hacker, you haven't had to pay millions or even billions of dollars in research and development to come up with the process. You just steal it. So it's always interesting in the manufacturing industry, what are some famous cyber attacks and background of high profile theft that's occurred that we've probably learned about? In fact, this example I'm going to show here are things that we saw a video about in preparing for the midterm exam that we had. There was an article that I found from Goldstein written in 2015 called Chinese Hackers Stole F-35 jet blueprints in a Pentagon hack. So the Snowden documents, according to this article, report that Chinese hackers stole literally terabytes of data about the F-35 stealth fighter jet, and many design elements of the Chinese J-31 contains many similar designs. So you can imagine being able to steal R&D funding, if the Chinese actually did this and implemented that into their design, could literally save them billions of dollars of R&D effort, and just by potentially copying another design. So taking another look at a very high profile case that we've also learned a little bit about this semester, you might be aware, of course, is the Stuxnet virus, which is a type of flame malware that was designed to increase awareness of Iran nuclear centrifuges through data collection. So Stuxnet also damaged the centrifuge based on that acquired sensor data. The article that I grabbed this from was an article from 2012 called Stuxnet Computer Worm Cyber Attacks Defeated in Iran. It's a really fascinating article, and I also wanted to show you a little bit of some of the code details of Stuxnet so you can see the flame underscore props, and perhaps that's how it got the name flame malware. Either way, it's a very sophisticated type of hacker or hacking attack that variations of Stuxnet have been subsequently used since it was released and imposed on the Iranian nuclear centrifuge program. So prior to taking this class and then through just general knowledge acquisition, I thought maybe Stuxnet was all there was out there potentially for very sophisticated malware that could be used to impose an attack on a facility by a bad actor, by a nation state, something like that. They're doing a little bit of research through a site called F-Secure. It turns out that there's also flame malware variants that are intended for Android phone systems. So that's where you get viruses like Shidun and Droid Kung Fu, which is the very similar Android malware. And essentially, this provides a framework for automatically downloading and installing undesired, new, and potentially malicious adware, whereas Droid Kung Fu is used to collect information from the infected device. Keep this bit of information in mind, because as we go into the study, you're going to start to see how an attack vector like Droid Kung Fu or Shidun could be utilized to facilitate a side channel attack like this paper discusses. So next, let's go ahead and talk a little bit about manufacturing industry and cyber attacks in particular. There's a high interest in discrete manufacturing processes. So think about processes where you might have equipment that's used to cut, grind, or chip excess material from a final product. Secondly, let's consider three different categories of cyber attacks in this industry. And we've already covered a few of them in some of the high-profile examples mentioned on previous slides. For example, intellectual property or process theft is one instance, manufacturing operations disruption, and the other one is product sabotage and reputation damage. Think about how Stuxnet ended up setting back the Iranian nuclear program by years. So On this next slide, let's talk briefly about what data can fabrication machines like CNC mills and 3D printers provide. First of all, the CNC mill and the 3D printer are both instruments that were used in the test setup, which I'll talk about in a little while. But essentially what the paper talks about is trying to define process parameters about these machines, like grinding wheels running at different speeds, or maybe the way that the wheel touches a particular object, or how does the grinding object, how is it moving past the wheel, or detecting varying grit levels applied to the object. If you think about it, all of those have different sound signatures. So for this study, they really focused on parameters like tool head location or direction with respect to the machine platform. But knowing these parameters' behavior has allowed the researchers to reconstruct forms as a sequence of tool head movements performed at various angles and distances. So now that I've provided some background on phones and the correlation between phones getting on the manufacturing floor and being potentially used to do a side channel attack, let's talk real briefly about collecting phone data to capture 3D printing material. So basically what the study did is by acquiring and using an audio signature library that they captured from the cell phone, capturing sounds the machine produces as it moves along an angle of interest. They actually broke it down full circle from 0 to 359 degrees and categorized those sounds. Then the researchers used a short time Fourier transform to reduce signal noise to provide a matrix of 2048 frequency points, and that number enabled sufficient resolution to reconstruct a shape, which is pretty impressive in my opinion. And then by collecting all these sounds, they create an audio signature library where they can determine and compare the gathered audio of a machine in action and reconstruct the most likely grind angle for each frame using correlation. You'll notice over on the right-hand side, I provided in the figure 4, which was taken from the paper itself, raw sensor data from the 3 axes of accelerometer and magnetometer while 3D printing a square. So the readings vary predictably, providing additional information not fully captured in audio recordings. So now that they've grabbed a lot of background data and created this audio library, they can use phone data to capture the 3D printing material, and let's talk a little bit about that more in continuation. By using a spectrogram, areas of interest and angle matches from the audio library, then the researchers in this paper demonstrate a 3D reconstruction of a printed star, first of all. So imagine just a three-dimensional star-shaped object. And they also included the option of having human assistance to create that based on the promptings that they got from the audio captures. The researchers were able to demonstrate how tool head changes can be detected. If you take a look at the band, the figure over on the right-hand side of the screen, when you see those yellow vertical bars shown on the right-hand side, those are representing or demonstrating tool head changes. So it's pretty phenomenal that something like sound could end up creating keys or information that you'd never know is valuable toward having a bad actor basically go in and reproduce what could be a very proprietary and expensively produced shape or some sort of device. So let's go ahead and take a look at the experimental setup for this study. If you take a look at what was figure 2 from this paper, you'll notice there's an attack setup. So for the phone attack, a phone placed on the same table as a 3D printer, and then you've got the CNC mill on the right. And so that phone records the readings of its sensors. And for the phone call attack, an attacker on the other end of the call records the call's audio itself. So let's go ahead and look at this a little bit more abstractly too. So the testing that was also conducted, they wanted to find the most optimal data quality using different phones or even considering a tablet. And it was really interesting because after they evaluated devices that I showed, I actually grabbed this from the paper below this table. they compared a lot of different cell phone types. And even though the paper didn't really go into detail why they chose the Galaxy S6 for the remainder of the study, I kind of have a feeling is it must have provided superior audio collection where they were collecting at 44,100 hertz audio sampling rate. I also wanted to point out on the right-hand side, there's a figure that sort of shows what the test setup looks like more abstractly. And you'll notice that based on their measurements, putting the phone in this case, it was a 135-degree angle, but imagine 45 degrees between the X and the Y axis in that top quadrant up there tended to be the ideal place where they could actually collect the best data. So a little bit more about data collection from the phone and the location, like I'd spoken about briefly on the previous slide. The researchers really wanted to determine the impact of phone distance to data quality while recording the same fabrication activity. It's kind of a good way to figure out where's the ideal place, and positioning it about equidistant from the X and Y motors provided an optimal accelerometer and magnetometer readings as shown in the graph below, where they compare on the y-axis normalized signal power versus distance in inches. So it's really interesting to note that the 3D printer and then the CNC mill each had a unique sound signature. So the researchers compared recordings of each machine, and here's what they found, that even though the mill and the printer's X and Y movements are driven by similar motors, the researchers could clearly identify the mill's movements based on the sound recordings, helping them make the machine sounds distinctly different, just based on audio recordings from the cell phone. And their results from this comparison suggest that a recording of a simple calibration pattern is about all that's needed to train either of their reconstructed methods. I wanted to also point out as well that here's some example spectrogram outputs shown on the right portion of this slide that show different patterns that you can see from local recordings of the 3D printer and the CNC mill, and then compare that with the spectrographs recorded via the phone call. It's absolutely amazing how much information can be gathered through this technique. So let's talk a little bit about the data quality in a phone call attack. Basically, what happens if the data was acquired during a cell phone call instead of deliberately setting the phone in a specific location, kind of like what we showed earlier, where there was a very specific location at 135 degrees at a specific quadrant between the 3D printer and the CNC mill. So they ended up even testing their side channel attack when two people were speaking, and all of the signals were a little bit noisier than in the deliberate phone placement example. The researchers could still reconstruct forms based on the phone call using similar techniques. So the phone call scenario really jumped out at me because even a casual conversation can be an effective attack vector to steal manufacturing floor secrets. It's absolutely amazing that just a phone call could actually cost a manufacturing company or some sort of a process or technique, literally millions of dollars of lost R&D. So how accurate were the reproductions? Well, let's give you a little bit of an idea of the framework that the researchers actually created using a software combination of MATLAB, a suite called Adobe Audition, and of course Python programming. They were able to create an interactive framework. And what was really fascinating is the team decided to recruit an electrical engineering master's degree student. She had no experience working with 3D printers or with audio analysis, just to try out the framework and see how well she could reproduce the results. So with a little bit of training, the student was able to learn quickly how to decipher the acquired spectrographs like I've shown in previous slides. And these are some of the results. So you might have a single winged image like trying to reproduce the shape of a B-2 bomber, for example, and then the 3D printing and then the reconstruction, you can see that the shape matches almost identically. Furthermore, there's design examples where they were able to reconstruct a star like we talked about earlier, or how about the general shape of a gun, for example. So you can see here, again, without a whole lot of expertise, you could have somebody go in who has bad intentions and steal a lot of intellectual property. So let's talk about what are the researchers' recommendations. They've obviously shown fact of function that this side channel attack is very effective. So then they started to try to come up with obfuscation defenses against the side channel attack that they discovered by playing music recordings on the manufacturing floor, in this case in the lab. What they found is that the attacker can still determine the shape of the item being manufactured. So obfuscation, though, can make the attack more difficult by making the hacker listener miss small details of the manufacturing process or from being able to accurately capture dimensions of a fabrication. So there is a degree of effectivity with that proposed defense. The team also hypothesized that using a set of played back recordings of people's voices that would actually make it peeling off these extraneous sounds away from the recording to get at the actual target data could make that side channel attack much more computationally and financially expensive. The team also posted sample data comparisons during obfuscation tests to post actual versus reconstructed value data. So take a look at this table over on the right that I grabbed from the paper itself, and you can compare a column of reconstructed and versus actual, and then the error margin between what was actually intended to be duplicated and what the side channel attack produced. So continuing with the researchers' recommendations, they also proposed another clever solution, which is to thwart a side channel attack by limiting the electromagnetic field generated by the manufacturing machinery by using better enclosures. So this solution is novel, and it could certainly raise the cost of a hacker reconstruction because it would make determining the quadrant angles much more challenging. Another interesting solution that they proposed is motor shielding. And what they proposed is actually using a polymer matrix composite, and that concerns manufacturers could act as an interference shield. There's several advantages of these kinds of shield, including the material itself is lightweight, it's resistant to corrosion, and it's modestly priced. So what were the conclusions to this study? You had a very in-depth, comprehensive study. The researchers, I feel like they gave a very good effort at trying to come up with proposed defenses that could be made against that. And I talked about some recommendations that they made. But in general, the researchers left a message to manufacturers. There's really some key things here. Things like factory floors, just knowing that they generate large quantities of proprietary data that can be stolen by adversaries who want to learn, about manufacturing techniques. The study itself focused on 3D printers and CNC mills, since additive and subtractive manufacturing, those are respective, tend to be layer oriented. Additionally, using a simple software framework that I talked about in a previous slide, a non-expert in the field can quickly train up to be able to exploit data stolen via a side channel attack. The other thing to remember is that mobile phones are everywhere, so the potential for bad actors to carry out this kind of attack, either through an insider deliberately placing a phone at an ideal location with side channel attack software preloaded, or just leveraging a phone call made by an unwitting victim, can lead to lost secrets. So because of these dangers, manufacturers must consider asking their employees and visitors to leave their phones at the factory door. Finally, the paper listed acknowledgments. Who funded this study? So this work was supported by the U.S. Department of Homeland Security through a grant to the National Science Foundation, and also through contributing funding to Singapore's Agency for Science, Technology, and Research, and through Human-Centered Cyber Physical Systems program. Very interesting paper.